Welcome back to The Explainer. I am absolutely thrilled to guide you through today's topic because we are taking on a pretty monumental task. We're going to translate the complex, beautiful mathematical models of astrophysics into the intuitive language of the universe. We're looking at the fundamental laws that govern, well, basically everything, from the falling of an apple right here on Earth to the life cycle of the most massive stars out there in the cosmos. We're going to take kind of a Russian doll approach today, zooming all the way from the grandest cosmic orbits down to the microscopic atomic engines that power them. If you've ever looked up at the night sky and wondered exactly how it all works together, you are definitely in the right place.
But before we start crunching the numbers, think about this for a second. How do we measure the temperature of a star we can never actually touch? Or how do we know what it's made of? Or figure out how fast it's moving away from us? I mean, we obviously can't send a thermometer light years away. The math and physics we're about to explore serve as the ultimate cosmic survival kit. It's literally the toolkit that allows us humans, stuck on this tiny rock, to decode the entire universe just by catching the light that happens to fall onto our telescopes.
Okay, let's dive right into this. Our agenda today covers 4 main layers. 1. Gravity and celestial mechanics. 2. Light, radiation, and spectra. 3. Thermodynamics of the stars. And 4. Nuclear engines powering stars.
All right, kicking things off with Section 1, Gravity and Celestial Mechanics. Let's start with the outermost layer of our Russian doll, zooming all the way out to the largest scales to discuss how massive bodies interact across the vast vacuum of space. Now, Newton's law of universal gravitation, F equals G times m1 times m2 divided by r squared, might look a little intimidating at first glance, but it actually tells a really simple story. The force of gravity just depends on the mass of 2 objects and the distance between them. The bigger the objects are, and the closer they are together, the stronger that invisible tether of gravity is between them. It is quite literally the fundamental glue of the cosmos.
And when that gravitational glue goes to work, it creates planetary orbits. And this brilliantly illustrates Kepler's third law, which reveals a really strict mathematical harmony here. The equation t squared over a cubed equals 4 pi squared over g times m plus m basically tells us there's an exact relationship between a planet's orbital period and its semi-major axis. In plain English, how far away a planet is from its star dictates exactly how long it takes to complete one orbit.
So, how fast do you need to go to actually survive in this gravitational arena? Well, there are 2 vital speeds you gotta know. Orbital velocity, the square root of gm over r, is the precise speed required to stay in a circular orbit. You're basically falling continuously, but you're moving sideways fast enough that you keep missing the planet. But what if you want to leave entirely? You need the escape velocity. For that, you actually just multiply by the square root of 2, giving you about 41% more speed. That's exactly what your rocket needs to completely break the chains of gravity and head out into deep space.
Let's move to Section 2 and see how this builds. Light, radiation, and spectra.
So we've established how massive planets and stars move. Now let's peel back another layer and zoom in to the electromagnetic light waves that are actually traveling between them. To understand starlight, we first have to understand an idealized concept called blackbody radiation. A blackbody is a theoretical object that absorbs all the radiation falling on it and then re-radiates that energy perfectly, based solely on its temperature. Now, while perfect blackbodies don't technically exist in nature, stars act a whole lot like them, absorbing energy and glowing fiercely in the dark. The heat of the star dictates the exact kind of light it spits out into the void.
Which brings us to 2 of the absolute most powerful tools in astrophysics. First, Wien's law, where lambda max times T equals B, answers our opening question. A star's peak wavelength tells us its exact surface temperature. A blue star is blistering hot, and a red star is much cooler. Second, the Stefan-Boltzmann law allows us to calculate a star's total luminosity just by looking at its radius and temperature, revealing exactly how much total power it's pumping out into space.
But light doesn't just tell us about temperature, it actually reveals motion. The Doppler effect for light shows us that when a galaxy is moving away from us, its light waves physically stretch out, shifting toward the red end of the spectrum. Observing this redshift, where z equals the change in wavelength over the original wavelength, which also equals velocity over the speed of light, gives us the object's exact speed. And guys, this is the literal proof we have that the universe is actively expanding.
Yeah, when light interacts with matter, the details get even richer. Think of Kirchhoff's 3 laws of spectroscopy like a cosmic barcode scanner. A dense, hot object gives us a continuous rainbow of light. But a hot, sparse gas, that only emits specific lines of color. Most crucially for astronomers, though, when a continuous spectrum passes through a cooler gas, like a star's atmosphere, that gas absorbs specific colors. This tells us exactly what elements are hiding in that gas. This interaction of light and matter is also responsible for scattering effects, like Rayleigh scattering, which perfectly explains why shorter blue wavelengths scatter across Earth's atmosphere and give us our blue sky.
Okay, zooming in even deeper now. Section 3, thermodynamics of the stars. We've seen the light the stars produce. Now let's look at the thermodynamic behavior of the stellar gases that actually generate that intense heat. At the very heart of the star is the ideal gas law. Pressure equals N times the Boltzmann constant times temperature. Why does this matter? Well, a star is essentially a billion-year-long war between gravity trying to crush the star inward and internal gas pressure pushing outward. As long as the temperature and particle density are high enough, that outward pressure perfectly balances the inward gravity in this beautiful standoff we call hydrostatic equilibrium.
But generating heat in the core is really only half the battle. That energy has to escape somehow. It fights its way out through three mechanisms: conduction in superdense dead stars, through direct particle collisions, roiling convection that boils bulk fluid just like water on your stove, and radiation, where photons literally bounce their way step by step from the core all the way out to the surface.
So, the crucial point is, where does it all start? Section 4, Nuclear Engines, Powering Stars.
We have finally reached the very core of our Russian doll. Where does all this relentless, universe-illuminating energy actually come from? Deep inside a star, the pressure and temperature are so extreme that atomic nuclei literally slam together and fuse. But not all stars fuse atoms the same way. The mass of the star completely dictates its engine. Stars smaller than 1.3 times the mass of our Sun use the proton-proton chain, which is a pretty straightforward process of slamming hydrogen protons together to make helium. Heavier, hotter stars, though, they use the CNO cycle, utilizing carbon, nitrogen, and oxygen as catalysts to facilitate hydrogen fusion way faster and a lot more violently.
Now, at this microscopic atomic scale, energy is quantized. According to Planck's relation, E equals h times nu, energy isn't just a continuous flow. It's delivered in discrete little packets called photons. And the higher the frequency of the radiation, the more energy that individual photon carries out of the star.
Now, what's really interesting about this slide is how slamming atoms together creates energy in the first place. The answer lies in Einstein's famous mass-energy equivalence, E equals delta m times c squared. When 4 hydrogen nuclei fuse into one helium nucleus, the resulting helium is actually slightly lighter than the 4 original hydrogens combined. That tiny sliver of missing mass, the mass defect, doesn't just vanish into thin air. Because the speed of light squared is such a massive number, even a microscopic amount of missing mass converts into an absolutely astonishing amount of energy. This is the exact mechanism that lights up the entire universe.
So we've zoomed from the majestic orbits of planets all the way down to the frantic collisions of subatomic particles, and we've seen how mathematics is the true language connecting absolutely all of it. From Newton's gravity to Einstein's mass effect, these formulas are the ultimate keys to understanding our reality. So I'll leave you with this thought to ponder. If these basic laws shape the fabric of the entire cosmos, what else can we unlock by simply looking up? Thanks so much for joining me on this explainer, and definitely keep your curiosity aimed at the stars.